Lecture for this session. Today we'll be talking about using algorithms from the C++ standard library. And so this is going to be a lot to do with more talking about iterators and things like that. And a lot of it's sort of seeing how we can sort of save our own time in using some of these algorithms instead of having to sort of put together our own loops and things, which you might think like, oh, you know, it's not a big deal, I'll just write it myself. But it's amazing how much time it takes to debug code in general. And so, you know, you might think, oh, it doesn't take much time to write the code, which is true. But then once you add in the amount of time it takes to debug it, then, you know, you may very well be looking at a larger chunk of time than you realized. And the nice thing about all these standard algorithms is that they've been pre-debugged for you. Okay, so that's one of the big advantages of using the standard library algorithms. Now, one thing to keep in mind, though, is that some algorithms are bigger than others. Okay, you know, the effort that it would take for you to re-implement them, you know, the big ones, it would take you like months. The little ones, you know, might only take, you know, a couple hours or something like that, right? So you get more bang for your buck when you're using the bigger algorithms. That being said, even some of the small ones are quite useful. All right. Okay, so the first thing we want to look at, this was an example from chapter 5, and now in chapter 6 we're sort of updating it. And so the idea is that we've got these sort of ASCII pictures that we're representing as vector of strings. Okay, each sort of row of the picture is a string, and then we've got a vector holding all the rows. Okay, and so some of the functions that we're looking at writing are being able to take two pictures and then concatenate them either vertically or horizontally. Okay. Actually, before I get too much further, I should get my drawing program running here. Need that a little bit later. So, you know, we've got, you know, we may have one picture like this, you know, with all these rows of strings, and then another picture like this, and then we'll want to combine those into one big sort of vector of strings. So this is the vert cat function will do that. And then there's also this horizontal concatenation function that takes two guys like this and combines them into one. So that's the horcat function. Okay? Let's look specifically at this, how we might be able to do vertcat using standard library. Okay, so here's the whole thing, and it's really just one line essentially. Okay, so here this is using the copy algorithm. Okay, and there's a bunch of stuff going on here. The basic idea of copy is pretty simple. You know, the way to think about it is you've got some sequence of things, and you've got another sequence of things, and you know, you're copying from one to the other, right? So that's what this algorithm is doing. Okay, so this is copy. Now, the interface to the algorithm, it takes the beginning of the first sequence. So it wants an iterator pointing to the beginning of that guy, and then it wants an iterator pointing, you know, just one past the end of that first sequence as well. So that's the first two parameters to copy. And then the third parameter should be the beginning of the second sequence. I'll write begin 2. Okay? And so what's happening over here is if we've got, you know, this top and bottom picture coming in, we're creating sort of our return picture, result picture, by just taking a copy of the first guy, of the top guy. Okay, so this is, here we're invoking the copy constructor there. Okay, and then the idea is that we want to add the bottom picture to the end of that ret vector. Okay, so what's going on here is that we're creating. Here's our ret vector over here. We initially copy that guy over, and then the idea is that we want to add all of these guys to the end of there. Okay. Now it might seem kind of funny that I'm saying, okay, how can we use copy to do this? Because in some sense, their destination over here doesn't exist yet. Okay. And so normally, like if we were to just say, let's say we were to put, ret.end as the argument for the third argument here to sort of specify the beginning of where we want to go, that would be like completely disastrous, and you'd cause like seg faults or even worse. Okay, and so we don't do that. Instead, we've got this other special thing going on. Okay, we use something called a back inserter. Okay, now this is a really new idea for you guys. This is something called an iterator adapter. Okay, so what this back insert function does is it's going to ask for, really what it's going to do is it's going to produce an iterator that's sort of a smart iterator, and it's adapting the actual return container. Okay, and what it's doing is it says, every time you try to write into me, I'm going to put that element on the back of the container. Okay, so it's this thing that looks like an iterator, but really it's sort of putting things at the back. Okay. So what's going on here is that we've got this back inserter that's adapting this return container, and sort of it's almost like making it look like it sort of goes forever in some sense. And as long as you keep writing things into that iterator, it'll just keep growing. Okay. Now there's lots of different iterator adapters out there. That's a pretty cool idea. So for example, there's iterators that take an iterator and make it look like it's been reversed. So like moving forward turns into moving backward and things like that. And we'll see an example shortly of how that's useful. Okay. Maybe in a little bit more depth. What's going on here is that there's an actual iterator class called back inserter, or back insert iterator. Let me do a new page here. I'll sort of sketch out what this thing looks like. Class back insert. Now I'm going to simplify this a little bit compared to what it really looks like. Okay. But I'm going to sort of specialize this for the particular situation we're looking at. But this is sort of the idea. So this iterator is actually going to sort of remember sort of a pointer to the underlying container, in this case the return container. So when you create one of these things, it's going to remember that. And then when you do something like, this is actually, it gets really fancy, but when you have an operator star, that's the dereference operator for the iterator. Because if you look inside copy, you're going to see something like, out. The main work is done by a line that looks like that inside of copy. Right. So it's saying dereference the sort of at the current position and increment to the next one, sort of all in one succinct statement there. Though you could, if you wanted to, you could unwind this a little bit and make it more clear. So what this star does, though, and then the trick is that it's this assignment that's going to actually make the write happen. And so what happens here is that this operator star is going to return this special proxy object. which is another class. It's probably going into more depth than you'd ever care about. And inside that proxy class, there's going to be an operator, there's going to be an assignment operator. In this case, it'd be like a string. And inside this assignment operator of the proxy, you're going to then actually do the pushback. So this is where the pushback to the container is going to happen. The proxy would also need a pointer to the container as well. So there's sort of like a whole bunch of magic happening inside of this iterator adapter. That thankfully you don't have to worry too much about the magic, but at the end of the day you just kind of realize, oh, I can take any container and make it look like it's an output iterator using this adapter. Cool. Any questions about that sort of whole process? Going back to the...
So all of that is going on in that copy.
Yeah. All of that magic is really happening sort of right there.
Okay.
That's sort of setting up the magic that's sort of setting up the magic. And then the rest of the magic is happening inside of copy where it does, this assignment here. And then that's sort of invoking all the magic to sort of do the pushback to that container. Yeah. So this kind of gives you a little bit of a insight into sort of like C++ is just such a powerful, flexible language that there's sort of amazing things you can do by overloading operators and template tricks and all kinds of stuff. And this is sort of gives you a little flavor of what library writers can do for you in that respect. All right. Maybe let's go on to the next example. So from last week, the other example that we didn't get a chance to talk about was splitting a string. And just going to sort of quickly sort of flash this by you. This is sort of what you're seeing here is the doing it all by hand version. Okay? And let me also tell you sort of what is this split supposed to do. So suppose you have a big long string, the brown fox, jumped, right? The idea is that we want to sort of split it up based on white space. So we're trying to sort of split it up like that and turn it in this case, turn it into 4 separate strings. Okay? So if you think about like algorithmically, what are we trying to do? You can imagine having sort of like, you just sort of want 2 fingers to keep track of where you're at. You'd have a finger sort of at the beginning, and then you'd sort of move the other finger to the first white space. So you need to sort of find white space as the first thing. And then that will be a word. And then next time around, you'll be like, okay, well, let's maybe swap fingers and try to go past the word, and then to find the next part of white space. Oh, and I should say it might be that there might be more than just one white space there. There might be like a whole bunch of white space, and we want to sort of skip over all of that and then start looking for the next word. Okay. So let's look at sort of that process using the C++ algorithm, the standard algorithms. So here's the version that that uses the STL, the standard template library. So here we are. We've got our string coming in. Then we're going to create our return. What we're going to return is going to be a vector of strings. Right? That's going to be the output of this entire process. Okay. Then we're going to sort of start off with one iterator, position pointing at the very beginning of our string. Now, what you'll notice here is there's this type def. I don't know if we've really talked about type defs before. So all a type def does is it just gives a new name to an old type. Okay, and this is useful when types get to be kind of long. Okay, and so for example, here you can say string, give me, what is your const iterator? Okay, what is your iterator type? Const just means it's the read-only version. All containers have both a read-write iterator, which is just called iterator, and then a sort of only readable iterator, which we call const underscore iterator. Okay. And so if you were to always have to write string : const iterator, that gets to be kind of a mouthful. So here we're just creating a nice shorthand name for it called iter. Okay, so now down here and down here we can just say iter I, and it's nice and short. One of the cool things about the next version of the C++ standard is there's this new way of declaring variables using the auto keyword. And then we could skip the type def and we just say like auto I equals s.begin. And so that'll be really slick when that's fully supported. Okay, so then we come into our main loop here, this while loop. And this is going to just, this loop is trying to process the entire string. Okay, and then our first job is to ignore the leading white space. Okay. So imagine, let's come back here. Imagine if our string, instead of looking like the above, looked like this. Where there's all this leading white space we need to ignore. So what we're going to do is we're going to try to find the first non-white space character. Okay? And voila, there's a function in the standard library called findIf. Okay? And what it does is it takes, so here's where we want to start our search at the current position I. We want to, go no further than the end of the string. Okay, so that's kind of what that parameter means, is don't go past this no matter what. Because you might not find anything, right? It might just be that the whole thing is one giant white space. Okay? And this tells it to, hey, stop at the end of the string. Now, this is the important part here. And this is sort of the findIf, the if part of the algorithm, is that it's going to apply this function over and over again. And the first time that this thing is true, that's where it's going to stop. And it's going to return to us the position or the iterator of where that function returned false. True. Okay. Let's see what that function looks like. It's pretty simple. So this not space function's up here, and all it does is uses the built-in is space function and then does a negation on it. So pretty simple. Okay. So at that point, once we'd run that findIf, now our I iterator is now pointing at the T in the. Okay. The next thing we need to do is to find where the white space starts again. That's going to be our J. Okay. Well, this is pretty simple. We do another findIf, but instead of not space, we're going to use a new function called space. Okay. This one's even simpler. It just calls isSpace. Okay. Now, my first reaction when I read this part of the book was, why on earth why not just call it, put isSpace directly? And why not put, that there? And not create this silly little function called space. Okay. It turns out that wouldn't literally work as is. Okay, and the reason for it is that the function isSpace is actually an overloaded function. There's lots of functions with that name. Okay, and the other thing to realize is that findIf is a template function. Okay, so it can work with lots of different kinds of iterators and functions and things like that. And it turns out that passing overloaded functions into template functions doesn't just work off the bat. There's ways to make it work, and this is one of the simpler workarounds to make it happen. There's other more complicated workarounds that I won't talk about today, but this is sort of the simplest workaround to sort of dealing with this combination of function overloading and templates. Just for fun, let's see what happens when we try to build it with this. We can take a gander at the error messages. Right. So sure enough, there's an error here, and it's complaining that there's no matching function call to findIf, and it's complaining about an unresolved overload function type. Okay. Invalid overload of is space. Okay. So it's sort of like, I don't really know what overload you're trying to use here, is sort of the gist of that. But then if we use a function that's not overloaded, there's only one space around, then we can build that and we're fine. And this is one of the things where, C++ is a fairly complicated language. This is why C++ programmers tend to be able to earn a good salary, is that it's not exactly easy getting trained up to use this language. All right. So at that point, after running that findIf, we now have our I and our j pointing, sort of bracketing a particular word. And now the idea is, well, now we want to copy just that word, this guy here, we want to copy it into our ret vector. And we're going to want to push it back so that we're going to have a vector that at the end of the day is going to look like this. It's going to be, close enough, the brown fox. Right. So we're going to be doing a push back on an initially empty guy to get the into the right position. And then we'll keep doing that with brown and then fox. Okay? So to do that copy, here we're going to, we're just doing a push back. And this is sort of a slick way of creating a new string out of a subsection of an old string. Okay? So this is just invoking the string constructor. And it turns out that there's many different string constructors. One of them takes an iterator range, a pair of iterators, the beginning and the end. Okay, so that'll create a new string, and then it'll push it back, push it on the back of the return vector, the ret vector. Any questions on that part? Seeing the constructor in this form is sort of maybe a little bit different from what you've seen before. Let me write it in another way, just as we could have instead written something like string, give it a name like temp, I, j, and then ret dot push back temp.
So in this vector, it's not necessarily first in, first out. It's doing it from the bottom.
So here we're just pushing it to the back. I mean, I could write it different ways, but one way I could write it, initially the return vector is sort of, empty. Okay. And then here this time I'll go.
I guess what's confusing me is the term pushback and then seeing the word the on top of your little stack there.
Yeah, I switched to drawing it, vertically, but here I'll draw it horizontally. So after having done the, let me get my. Oops. Okay, so here's like the return and it's got sort of no elements in it, okay? And then after doing pushback of that first time, it's going to look like this, right?
Okay.
So after sort of ret dot pushback of temp, where, this time around temp has the in it, right? And then next time around it'll have like fox, right? It's going to do another ret dot pushback temp again, but now it's going to have fox in it. And then at that point it'll the and fox would be what the, this is the return vector, sort of as we proceed through time.
Okay, I'm just hung up on just the term pushback.
Yeah, so
I
just
understand what's going on.
Yeah, so just mean, it's referring to the back of the vector as,
Oh,
that end.
Okay, now.
Right. So here it's a sort of back front doesn't make any difference. They're sort of,
Right.
but then here if you were to, there is also a push front, and so if you were to instead do a push front from here, like let's say what happens if instead you did a
Push front.
What you would get is fox
Okay.
the.
So it's taking the container and either pushing it back or front.
The new thing either goes at the front or the back.
Right.
Are you going to the
That
back of
makes
the line
sense.
or the front of the line?
Okay, now
Yeah.
that makes sense. Got
Yeah.
it.
Yeah. Cool. All right. So kind of going back to the, and wrapping up here on this example, you can kind of see that, this algorithm really has, just sort of 3 simple steps to it, and we can implement each step just with a call to a standard library function. And so, when you see the find if, an experienced C++ programmer is going to be quite familiar with those algorithms. So he'll be able to read this code really quickly because he'll be like, oh yeah, I know what find if does. I know what, pushback does, and so it's like boom, boom, boom. I can read this and be like, okay, I know exactly what's going on. And so this kind of raises the level of abstraction that you're working at, getting closer to like almost feeling like a scripting language kind of thing where you're sort of doing larger operations at a time. Okay. All right. Got another small example here. Back to palindromes. This one is really slick. A one-liner palindrome. Okay. So if you remember, a palindrome is a word that if you flip it, it's the same word. Okay. So an example would be like civic. Okay. You can flip that around, and it's exactly the same. Okay. So over here, there's a standard algorithm called equal. And the job of this equal function is just to take 2 sequences and sort of march through the elements of the sequence, checking to see if they're equal. Okay. Just to sort of be very explicit, the generic picture you should have in your head for this algorithm is that you've got these 2 sequences, and it's just sort of doing, are the first things equal or the second things equal? And if it turns out that everything's equal, then the overall algorithm will return true. Yes, these are equal. And if there's just one difference somewhere, it'll return and say false. They're not equal all the way through. Okay? So now let's look at what we're doing here. So imagine, that W here, that we've just typed in civic or something like that. Okay, what we're going to do is we're going to pass in the beginning and the end, okay, of our first of that sequence. Okay, so that's sort of generically, that means that we want to tell the algorithm again the beginning and one pass the end of the one sequence, and then we also need to tell it the beginning of the other sequence, right? But in this situation, we're going to do something a little bit different. We're going to use r_begin. Okay. Now r there is for reverse. Okay, and so what we're actually doing there is the RBegin iterator is actually pointing to this spot back here. And then when you tell that iterator to move forward, it's actually going to move backwards instead. Okay? So, like, I think one of the solutions I saw I gave to you guys previously, we actually went and physically reversed the string, created like a new string that uses a whole bunch more memory, and then physically reversed it. Here, we're not creating any more memory or doing anything. We're just sort of on the fly reinterpreting this thing to go backwards using this reverse iterator. Okay, so what's going to happen? So let's sort of walk through what happens with Civic. So, and let's you make up a name here. Let's say our I is the iterator that's being used inside of equal for the one side, and maybe J is the one for the other side. And so I is going to be pointing to the initial C. But then because we've got the RBegin, this J, will be pointing to this guy. And it's going to say, are they equal? Right? And then it's going to move them both forward, but this guy's a reverse iterator, so that's going to mean backwards. And it's going to ask, are those things equal? Question?
So does RBegin automatically begin at the end of the string as well?
Yes.
Okay.
Yep. And the REnd will give you sort of what would actually be down here. One past the beginning, actually. And so you can just pretty much pretend that once you have RBegin and REnd, you've got the same container, except that, it looks like it's been flipped around. Okay? Right? So then I and I is equal, and then they'll both be pointing at V at the very end. That'll check, and then it'll stop at that point. No, it won't. I lied. It'll keep going, actually. They'll both go all the way to the other end. So in some sense, maybe you might think, oh, this is a little bit overkill. Like you might, instead of saying going from WBegin to WEnd, you might say like, oh, let's just go halfway or something like that. Okay. So you could imagine optimizing this further, but then it might not be just a nice one-liner. But yeah, so this is kind of a neat example of doing reverse iterators. So kind of a little bit again under the hood with that RBegin. There's this class called, reverse iterator. And it has, a data member inside of it called real, that's the real iterator. Real iter. It has some type that I'm not going to worry about. And then, the gist of it is that when you do operator like plus plus on the reverse iterator, that's going to end up doing like a minus minus to the real iterator that's underneath it. Okay, so that's just sort of the gist of what's happening in terms of the code. All right. Any other questions about the reverse iterator and this equal function? Okay, we've got one more example to talk about. This one's a little bit bigger. It's getting back to the student grades. And it's sort of, let's pull that project up. So at the top of this, we've got all the code from last time, where we were doing things like computing the median homework, and we were using that as the homework score. And we had done things like group together the student infos into a struct and all of this stuff. Now, what's sort of funny about the median is that, let's say you're a smart Alex student. You might do something like, well, shoot, how can I really easily get a really nice high median score with very little work? You guys think of, if you're being smart alecky and you knew that the instructor was going to take the median of all your homework scores, what could you do?
Yeah, so if you get really low grades on the first couple, you can just not care.
Yeah. In fact, you could sort of like not do like almost all the homework. You could do, I think what it would take, you just need to do two real homework assignments and do well on those, and then get zeros and all the rest. And the median would still be like, let's say you got slightly lower on one of the homework scores. Your grade would be that slightly lower grade, right? So here, all right, what's the median of 0, 0, 0, 0, 9, 10, right? Oh, no, that's not quite right. You need to do like half. Yeah. So let's say, then you got like 9, 10, 10 or something like that. Or maybe one more, right? So then this would be the median. Yeah. So you could basically get away with doing sort of not doing half your homeworks, okay? So, and I think this actually happened to the authors as they were teaching their course one time. Like a whole bunch of students were gleefully like saying, I'm done. I've already done half the homeworks and I'm doing well enough. So then what the instructors wanted to do was to create some analyses to sort of look at all the homeworks and try to figure out what's going on, but sort of automate the analyses, okay? And so what they ended up doing was they wanted to look at a couple different grading schemes and see if the students would do drastically different using different grading schemes. So the first grading scheme is just the one that we're already used to, that uses the median, okay? Median of the homework grades. And then the second one is, let's look at the average of the homeworks and use that as the homework grade. And then the third one is, this is actually kind of, this one sort of is going even easier on the students. And it's just taking the median of the homeworks that you turned in. Well, I don't know. So, I guess this is, I'm not sure why they're adding this analysis. I mean, I think the average one is the more important one, because with the average, all these zeros are going to drag down your average quite a bit. But anyways, these are the three analyses they wanted to do. So they wanted to sort of recompute the grades using these three analyses. And then what they wanted to do is, they didn't want to sort of, let's say you've got 1,000 students, they didn't want to look at, all 1,000 numbers, times 3, okay? So then they wanted to have sort of distill the results from all the students down to one number and compare those. So then what they wanted to do was to take the median of sort of all the student scores, just the median grade in each of these three scenarios, okay? So you compute your homework grades and then just sort of look at the median student score across the whole thing, okay? Now, one thing that's kind of interesting about this is it starts to look kind of repetitive, okay? Like, we're going to sort of do a similar kind of analysis on every set of homeworks, okay? So one of the things I want to show you in this example is how can we sort of use a smart programming technique to sort of avoid duplicating our code, given that we're doing sort of three things that are quite similar. Okay, so we'll see how that goes. Oh, the other thing they wanted to do was they wanted to split out students into two groups. The students that did all of their homework, and then the students that sort of, slacked on at least one homework, one or more homeworks. So we're going to sort of break these into the dids and the didn'ts, okay, in terms of did all their homework. Okay, so first we need to, kind of breaking this down, let's start to think about what are some little functions we can create that sort of handle some of what we want to do, okay? So the first thing here is, how do we check to see if a student did all their homework, okay? Now, And let's assume that when they don't do their homework, then they get a 0 in the grade book for that, okay? So here, oh, and I guess one other caveat, I mean, how could you tell between like they just did abysmally poor versus didn't do it at all? And so it turns out that the way the instructors did this is that even if you turned in the homework, you'd always get at least a 1 or something like that. You get some partial credit for like putting your name on the page. Okay, so with that explanation, this function did all homework makes sense. Okay, so what it's going to do, it's going to use the standard find function, and it's going to look for a 0. Okay, and this find function is actually going to return with the position where it found a 0. Okay, if it found one. If it doesn't find the thing it's looking for, it's going to make it all the way to the end and return an iterator pointing at the end. Okay, so that's why we can use this equal check here. Right, so find is going to return some iterator. If it's equal to the end, it means it never found the 0. If it's not equal to the end, then it did find a 0, right? So what we're looking for is doing all your homework means there's no zeros, means that find went all the way to the end, never found anything. Okay. Now let's look at rewriting our homework analysis functions, or functions that sort of actually no. Let's look at. Suppose we already know how to compute the median of all the homework of the homework for a particular student, right? And now what we want to do is like compute the grades for all the students and take the median of that. Okay, and let's see how we can do this sort of in the most succinct way possible. Okay. So here's this function called median analysis. Okay, we're going to input a vector of students. And the first thing we want to do is compute the grades for all the students in one big batch. Whoa. Here we're going to use a function called transform. Again, another standard function. Okay, let me draw a little generic diagram showing what transform does in general. And then we'll talk again about how it does what we want to do in particular. So this is transform. Let me make sure I've got this. Yeah. So the idea with transform is that you've got some sequence coming in as input, and you also have a function. Okay? And suppose, let's say, just for kicks, that the thing inside, here were like apples. Okay? And then let's say you have a function that can turn apples into oranges. Okay? Then what this transform function is going to do is it's going to create a new sequence. Let's see, this is, apple A, B, and C. Then what is going to be put in here is the function f applied to A, and then the second element here is going to be f applied to B, and so on. So transform is going to march through the sequence, applying the function that you gave it to each element, producing a whole new sequence. Okay. So now let's think about, well, how can we apply this to students and grades? Well, we've got this vector of grades that we want to create. We're going to send in our sequence of students. Okay. The output is going to be a back inserter to the grades. And then the function that we're going to pass in is this grade auxiliary function. Okay? All this auxiliary function does is it just calls the grade function. With one caveat, if you remember, there's a problem when of computing the median when there's like 0 homeworks in the vector. So that's why it would then throw an exception. And so that's why I've added this catch clause to say, okay, go ahead and just consider the homework grade to be 0 and, compute the grade that way. Okay? So here we're passing in this grade function. So transform's going to compute the grade for every student and push it to the back of the grades vector. And then at the very end there, we just have to compute the median. That's one of the functions that we created earlier. Compute the median of all the grades. So that's the median analysis function. Let's look at the same idea, but now for computing the average. Okay? So here, we're doing almost exactly the same thing as before. But now, instead of using sort of the median, we want to compute the average grade for a student. Okay? But everything else remains exactly the same. That's the only thing that differed is the part that I've got highlighted there. And now let's say, okay, well, how do we compute the average? Well, this is really slick. Well, we want to compute the grade, but we need the average of the homework, so we're going to create a function called average. And here we're going to use a function that's also from the standard library called accumulate. So let me again tell you what accumulate does generically. And perhaps the easiest example for accumulate is the following. So suppose I have a sequence of numbers, like 1, 2, 3, 4, 5, 6. That's our input. You also have to give accumulate a sort of seed value, which in this case, let's use 0. And you also have to give it some kind of function that takes two inputs and somehow combines them and gives you in this case, like a number output. So, for example, using addition would be sort of a good thing to use with accumulate. Okay, and if you call accumulate with these arguments, then what you'll get at the end of the day is, well, what it's going to do is it's going to take the first two numbers. It's going to take the first number and add it with 0. Okay, so 0 and 1 is 1. And then it's going to take that number and add it to 2. So you can get 3. Then it's going to add in 3. You can get 6. Add in 4 to get 10. Add in 5 to get 15. And then add in the 6 to get 21. So your final result there will be 21, which is just the sum of the... Did I make a addition mistake? Or no? Okay. So you'll get the sum of the numbers in that sequence. Okay. When I use sort of addition and 0 as sort of the inputs to this. Okay. I could have used different inputs. So for example, what if I wanted to produce the product of the numbers in the sequence instead of the sum? I could instead use multiple